Hello everyone, welcome to the Gravity channel. By now, you might have come across a lot of circuits consisting of capacitors, resistors and all. So there are complicated circuits in which you need to take help of Kirchhoff's law or other complicated circuital loop laws to solve them. So today I am going to discuss simpler methods to find out complex resistances and complex capacitors. So by complex I don't mean alternating, by complex I mean complex circuits. So resistors and capacitors in complex circuits can be calculated by simple methods. So the method that I am going to discuss today is called StarDelta Method. That is the popular name. It is also called as Wye-delta. So the name goes as StarDelta Method for electrical circuits. So basically, this is the symbol for StarDelta. So we'll take an example to see what this means to us. So suppose we have given a circuit. So I shall name the points A, B, C, D, F, and G. So now suppose we need to find out the total resistance for this circuits between the points A and D. So as you can see, there is no Wheatstone balancing, that is 1:4 and 2:5 are not the same thing. So this BF branch cannot get cancelled. So the usual method to solve this is using Kirchhoff's equations, the loop law and the junction rules. Okay. So instead of using the Kirchhoff's rules, we can use the StarDelta method. So first I'll write the equation for the StarDelta method, then we'll see what do they mean. Okay. So by using the StarDelta method, we need to find a junction having three resistances. So here we have two junctions like that, having three resistances. Junction B and junction F. So the junction has three resistances connected to it, 1 ohm, 2 ohm and 3 ohm resistances. So this is our star. So this is B junction. And this is out of view. So for now I'll name them as R1, R2 and R3. This can be converted into delta. So here instead of junction B, we convert this whole circuit into this way, delta B. So let me write them as RA, I'll make this RA. RB and RC. So we are going to convert a 3 resistor junction into a triangular resistance circuit. So the way to do the formula for this is, so we have to calculate RA as, RA will be, first we multiply pairs of 2 and then add them. This is R1, R2 plus R2, R3 plus R3, R1. So we are finding RA, so we divide this with the opposite one. So the opposite to RA becomes R1. So we can visualize like this. So this is RA, so we have to divide this by R1. Similar process should be done with RB. So the numerator has Rij, where I and j take value from 1 to 3 and I never equal to j. And the denominator Rb, so this is Rb, so the denominator should be R2. Same for Rc, so R1, R2 plus R2, R3 plus R1, R3 divided by R3. So we'll convert this B junction, the three resistances, into a triangle circuit. That will simplify a lot of things for us. So I would like you to note these down because I am going to transform this, so I need some space for the ruler. I am going to rub these. Okay. So you may pause and write this down, or I will give all these formulas at the end of the video also. So I'll keep this one for reference. So now what we are going to do is, we are going to modify this circuit a little bit. So into, we are going to modify this. So we can imagine this, we can bend this circuit like this. So this is the same circuit. This is our junction B. Now instead of this junction, we are going to convert this into some resistance. Let's call this RA. RB. RC. So once we convert this junction into the triangle, into the delta, we can rub this thing. Okay. So according to formula, we can find the RA becomes the product 2 plus 6 plus 3. The opposite resistance to RA is 3. So this becomes 11 by 3. So 11 by 3 is down to 3.6, and 6 will go on recurring, so 3.67. So RA becomes 3.67. Similarly, we get RB to be equal to, so the numerator will be same, 11, and opposite to RB is 2. So this is 5.5 ohm. So RB is 5.5 ohm. RC, so this RC is going to be 11 by opposite 1. So RC is 11 ohm. So here we have converted this junction into this triangle. So now we don't need that junction anymore. So I'm rubbing it off. So the circuit is simplified. So we can see this circuit is simply like this, 5.5, 4, 11, 5, this is our point B, and parallel to these we have 3.67. So now this one becomes a series parallel connection. So here we can see 4 and 5.5 are in parallel. We can calculate the parallel for this. So I'm rubbing this off. So let's call the parallel of this as R1. So or Rx, you can call them anything, RP, RQ, calling them RP. So this is 5.5 into 4, 5.5 plus 4. So this becomes 22 by 9.5. So this becomes 2, 3, 1, 6 ohms. So the parallel resistance comes out to be 2.316. Same process for 11 and 5. So let's call them RQ. So 11 into 5, that is 55 by 11 plus 5, that is 16. So 55 by 16. So 55 by 16. This comes out to be 3.16, 4, 3, and 7. This is enough. So this can be written as 3.44. So 3.4375 to be precise. So this can be written as 3.4375. Now 2.316 and 3.4375 are in series. So the series connection comes to be RS 2.316 plus 3.4375. So this comes to be 5.74 and 5. So 5.75. So I'm rounding this up to 5.75. So we have only two branches left now. So the one is upper branch 3.67 and the lower one is 5.75. So 3.67 and 5.75. Okay. So do the calculation here. So the final resistance, net resistance is 3.67, 5.75 by 3.67 plus 5.75. So this comes to be 3.67 into 3.67 divided by 9.42. So we cancel this. So 3.2 cancel this. So this comes out to be 2.24. So the net resistance for this circuit is 2.24. So we came to this solution 2.24 simply by transforming the circuit. Okay, this is way simpler than the Kirchhoff method. Okay, so there is another method of doing this, which is the inverse of star delta. It is called the DeltaStar Method. Okay, the DeltaStar Method. So the second method to do this is DeltaStar conversion or Delta-wye conversion method. So the formula for this we shall note. So suppose we are given a triangle arrangement of resistors. Let's call them R1, R2 and R3. We wish to convert them to a Y or a star shape. So let's call these RA, RB and RC. So the formula to do this is RA. So you can see RA will be here. So RA has R2, R3 divided by the sum of all three. And so goes for RB. RB becomes R1, R3 divided by the sum. RC becomes, so R1, R2, you would have guessed by now, divided by the sum. So again, mind you, so these formulas are derived from Kirchhoff's itself, from Kirchhoff's rules. So but instead of using Kirchhoff's rules over and over again, we can use these and simplify our circuits. So we'll take the same circuit, the last one circuit, so that way we'll verify the answer also. So the circuit was 1 ohm here, 2 ohm, 3 ohm, 4 ohm, 5 ohm and so on. Okay. So we will name them A, B, C, D, A, B, C, D, E, F. Okay. So now we are going to convert a triangular to a star shape. So we need to find three ends. So we have three ends. Between B and C we have 2. Between E and C we have 5. And between B and E we have 3 ohm. So we can redraw this very circuit like this. So we are not changing anything. So this is our 2 ohm resistor and this is our 5 ohm resistor. So we can see we have a triangle here. So we are going to convert this triangle to a star. Okay. So what was the name for this? C or D, same thing. So now we will name these to be RA, RB and RC only. So let this be RA, let this be RB let this be RC. So RA is the adjacent ones, so that is 3 times 2, and 3 plus 2 plus, we have 5. I have written 5 by mistake. So 3 plus 2 is 5. So this is 6 by 10. So 0.6 ohm. So RA is 0.6 ohms. RB is 15 by 10, so 1.5 ohm. So this is 1.5 ohms. RC is 10 by 10, so 1 ohm. So this one is 1 ohm. So we can redraw this circuit as, shall I rub this? I'll rub this itself. So we can remove the triangle now. We don't need these. We don't need this. So now we have a simplified circuit. So again, this becomes a series parallel case. So RC, this is 1 ohm. So now we can see that 1 and 0.6 are in series. So the series connection for these becomes 1.6. 4 and 1.5 are in series. So their total becomes 4.5 ohms. Now 1.6 and 4.5 are in parallel. So the parallel value comes to be 1.6 times 5.5, sorry, this is 5.5. 1.6, 5.5, 1.6 plus 5.5. So this is 1.6 times 5.5 divided by 7.1. So this comes to be 1. So 7, 5.5. So this comes to be 7. This comes to be 1.239. So this entire circuit between point A and point G is 1.239, and then we have 1 ohm in series with it. So 1.239, this entire thing, plus 1 ohm. So we have 2.239. So the net resistance is 1.239 plus 1. So 2.239 ohms, approximately 2.24 ohms. So this confirms our last method too. Okay. So you can see that these methods simplify the circuits. So there is no need to use Kirchhoff. But obviously Kirchhoff's law has to be used for your board exams. So you can use this to simplify the circuits in case of solving MCQs or giving entrance exams. So these methods have become very handy. So these were relatively simpler circuits. In very complicated circuits where you have 3 points or a triangle at multiple places, you can simplify any one, and the entire circuit gets down to series and parallel connection of resistors. Okay. Meanwhile, I'm also giving the Kirchhoff solution for the same circuit. So this 1, 2, 3, 4, 5 ohm circuit. So you can pause the video and note that down. Okay. Okay. This ends our resistance section. We can use similar formula for solving capacitor circuits also. Okay. So this is end of part 1. So in part 2, we are going to continue with star-delta conversions of capacitors. Okay, so star-delta conversions for capacitors now. So the star-delta formula for capacitors is the delta-star formula for resistors. So as expected, wherever there is R up, the similar formula for C is down. The C is placed to be down, and vice versa. So again, we are going to find a junction having 3 capacitors connected. Let's call them C1, this is C2 and C3, and we are going to convert this into a delta or a triangular arrangement of capacitors. So this is C, C, CA and CB. So the formula goes like this. So star delta is CA is the delta star for resistors. So that is C2 C3 by C1 plus C2 plus C3. CB is C1 C3 by C1 plus C2 plus C3. CC is C1 C2 by C1 plus C2 plus C3. So we take similar arrangement. So this is 1 farad or 1 microfarad capacitor. We'll take 1 farad, doesn't matter. Three farads, 4 farad, and 5 farad. Okay. So this is our junction. So let's name them A, B, C, D. So we are going to convert this junction, we are going to convert this into a triangle. So I am passing the triangle from above. So 1F and 2F. So I am passing it like this. Okay. So this is our CA, CB and CC. So CA is going to be 1 times 3. So this is 1, 2, 3 divided by the sum plus 2 plus 3. So this is 3 by 6. So that is 0.5 farad. CB is 6 by 6. So that is 1 farad, and CC is 2 by 6. So this is 1 by 3, so that is 0.33 farad. So now we have converted this circuit, so now we don't need our star anymore. So let's get rid of it. Okay. Now this becomes a simple case of series parallel connections. 0.5 farad. So 0.5 and 4 capacitors are in parallel. So their total would be 4.5. So let's call this Cx. So Cx is 4.5. Cb was 1. Cb is 1 farad. And Cc is 0.33. So this is 0.33. This becomes 6 farad. Now 4.5 and 6 are in series. So our series becomes 4.5 times 6 divided by 4.5 plus 6. So this is 4.5 into 6 divided by 10.5. Yeah, so we might cancel them. So 5, 1, 5, 10. So 5. So this becomes 2.57. So we have a lower branch, this is 2.57 farad, and an upper branch, that is 0.33 farad. So the net capacitance, the total capacitance would be 2.57 plus 0.33 farad. So this is 2.9 farad capacitance. So again, if we wouldn't have used this formula, we would have to use Kirchhoff's rules. Okay, so now we'll try to do the same using delta star conversion. Okay, so method 2, delta star conversion for capacitors. Okay, so now method 2 for capacitors, the delta star for capacitors. Okay, so delta star conversion for capacitors. So as expected, the formulas will be that for star delta for resistors. So here C1 is going to be the product CA CB plus CB CC plus CC CA divided by the opposite to C1 is CA. So this is C1. C2 is going to be again CA, CB plus CB, CC plus CC, CA by CB, and C3 is going to be CA, CB plus CB, CC plus CC, CA by CC. Okay, so we'll take the same circuit. So 1 farad, 2 farad, 3 farad, 4 farad, and 5 farad. So now we have to find a triangle. So a delta. So this is our delta. Okay. So we are going to convert this delta to a star. Okay. So let's call them. So this is C2, this is C1 and C3. Okay. So we'll find individually all this. So C1 is, as we can see, the product of 2, 3, 3, 5 and 2, 5 divided by the opposite to C1 is 2. So this comes to be 6 and 15 and 10. So 31 by 2. So this is 15.5 farad. So C1 is 15.5. C3 is 31 by, opposite is 5. So this is 6.2 farad, and C2 is 31 by 3. So this is 10.33 farad. Okay. So we don't need the delta anymore. So I'm rubbing the delta off and substituting with this star. So again, this has come down to a series parallel conversion. So where C1 is 15.5, C3 this is 6.2, and C2 is 10.33. From here it's pretty simple. You can see these are in series, 1 and 6.2. So for series, so let's write this as Cx. So Cx is 1 into 6.2 divided by 1 plus 6.2. So that is 7.2. So this comes down to 8, 6, 1, 1. Okay, same process for 4 and 1.55. So let's call this Cy. So Cy is 4 times 15.5 by 4 plus 15.5. So that is 19.5. So this comes to be, so 5 is cancelled here. So this side and 6. This comes out to be 3.18. So the upper branch is, what is it, 0.8611, and the lower branch is 3.18. These are in parallel. So the parallel resistance for these is 3.18 plus 0.8611. So we are rounding this off. So this comes to be 4.04 farad. And this 4.04 farad is in series with 10.33. So the net resistance comes to be 4.04 times 10.33 by 4.04 times plus 10.33. So 14.37. And this comes to be, let's look this off. So 404, so 47. And these 4, 3, these comes out to be 2. So yeah, so exactly 2.95. So the entire resistance comes to 2.9 farad. So the same as last result. So even for this particular circuit, for the arrangement of capacitors, I have solved this using Kirchhoff's also. So you can pause this video and watch the Kirchhoff's method. Okay. So I hope this helps everyone. So here we simplified 3 resistor or 3 capacitor junctions or triangles to simpler circuits. So even big complicated circuits which have a junction containing 3 resistors or capacitors can be solved using this. So what you have to try is convert them to series parallel, and then from there the road is pretty simple. The path is the same. Okay, I hope this helps. So these are all the formulas put together. I'll let you have a closer look. You may pause the video and note these down. Okay, I think it's enough time. So we are ending this video. So let's hope this simplifies your calculations, your solutions, and particularly for MCQs and for entrance exam, these methods are very useful. Instead of using the long equations for Kirchhoff's, you can use this and simplify your circuits. Okay, so we are ending this video with this. So today's quote: the initial struggle has to be tough, but if you learn from it, if you struggle smartly, the consecutive struggles can be simplified. Thanks for watching.